Everybody, welcome back to Tech Junior Tutorials. My name is Lee Warwick Jr. and we're doing Advent of Code. Today we're going to be talking about day 16, which is probably one of the hardest days so far. It's kind of funny, it's the shortest amount of code I think that I've seen, and that seems to mean like that's going to be a really hard puzzle to solve. Shout out to Coding Blocks. That Slack channel really helped me out with this one. A couple of the guys on there are doing Advent of Code with me at the same time. So whenever I get stuck, I jump on there, I jump on Reddit or something, and I look around and see if I can find some hints or see if there's anything that I can uncover to help me get through the puzzle. And that's what I had to do for day 16, part 2, which is an absolute nightmare. So let's jump right in and check out this puzzle. So today is actually day 18, and I'll be working on 17 and 18, but as we get closer to Christmas, it just becomes harder and harder to spend time on these code puzzles because they are pretty dang difficult and they take sometimes hours to crack. So with that said, let's check out day 16. This one is called Flawed Frequency Transmission. So you can see that there is a absolute ton of stuff to read for this one. But if you look at the code, here's my code for the solution for part 1. It is 31 lines, including some examples. And then part 2 is about 38 lines, including some examples. So you would think that that would be easy, or it means that it's easy. It was not. So let's actually dig into the directions real quick. So they say that you're going to get an input, and that's going to be a list of numbers. And it's going to be basically a string. So if we look at the input for today, it is just one long string of numbers. So there's no comma separated values or anything like that, just one long string. And what they say is that for this string of numbers, you're going to need to calculate the new signal. So they say the string of numbers is a signal. And it goes through a phase, and that's like some set of calculations. And then each phase, it becomes a new number. And then the next phase is going to use that number for its calculation. And so they say after 100 phases, they want you to figure out what the number is. So there's a pattern to to how this works. And it is based off of this 0, 1, 0, -1 pattern. So if you look at this much shorter example, just in general, you can see there's like a real wealth of test data because I think this one is so dang hard. But if you look at this example with 1, 2, 3, 4, 5, 6, 7, 8, basically what you're going to do is you're going to take that pattern of 0, 1, -1, or 0, 1, 0, -1, and for the signal, you're going to calculate a new signal that is the exact same length as the old signal. So you can probably already guess that this is a very complicated set of instructions that we have to follow, and that is what makes this so difficult. So if you start here, that's your input before a phase. After one phase, it's going to become that, and then after 2 phases that, 3 phases that, so on and so forth. So it's always going to be the same amount of digits, so 8 in this case. And then for each digit, you're going to loop over the entire set of numbers. So for digit 1, to calculate the new digit in place, the first digit, I guess. It's hard to even talk about this one, but so to get this new digit of 4, you're going to loop over all the numbers. So you're going to do, for each number, 1 times the phase pattern up here. So for the first digit, it's going to be that same base pattern, except shifted over 1. Right? So what that means is you're going to start at 1, and you go 1, 0, -1, 0, 1, 0, -1, until you're done with the list. So there you go, 1, 0, -1, 0, 1, 0, -1, 0, and then the numbers that you're multiplying these by are each number in the list. So 1, 2, 3, 4, 5, 6, 7, 8, all the way down. So you multiply those all together, or multiply each one, then add all of those products together. So 1 times 1 is 1, plus 2 times 0 is 0. So 0 plus 1 is 1, plus -3 is -2, plus 0 is -2, plus 5, so on and so forth. If you add all that up, you should get 4. And then for the next one, so for this digit now, to get this 8 over here, we're going to use that same base pattern, except we're going to extend it by 1 extra. So we're going to repeat. So instead of doing 1 and then 0, we're going to do an offset of 1. So basically, this is going to become 0, 0, 1, 1, 0, 0, -1, -1, and then you're going to move over 1. So you're going to start at 0, which you can see here. So 0, 1, 1, 0, 0, -1, -1, 0, and that would keep going. But we ran out of digits here. So that gives you 8 when you add all those numbers together. And so you do that for each number in this signal, and then that should give you 8 new digits to do. So your challenge is to calculate after 100 of these, so loop over this 100 times, and figure out what the phase is going to, or the input signal is going to be after 100 phases. So they give you some moderately larger signals. They say like, okay, after 100, this becomes this. And the very last thing they kind of throw at you is that they don't actually care about these other numbers. They only want to know the first 8. So 1, 2, 3, 4, 5, 6, 7, 8. So they want to look at, after 100 phases, these 8 numbers. So after you loop over this 100 times, you're going to do like a slice, grab the first 8, and that should give you this. So if we check out my code for this, when I first did this, I had for loops all over the place. I was calculating the phase pattern for each pass through, and long story short, in refactoring and trying to figure out part 2, which we'll talk about in a second, I landed on a much faster way to do it. So instead of looping over each digit or each, so if you have 8 digits, you're going to make 8 phase patterns. Instead of making 8 lists of 0, 1, 0, -1, 0, 0, 1, 1, so on and so forth, I just basically landed on a formula for it. Don't ask me how I figured this out, but in my Zen programming, smashing my face against the desk, trying to figure out part 2, landed on that if you're going to loop over each phase, right? So from 0 to 99 in this range phases, if phases is 100, I don't care about that index. I just want to do this 100 times. So for each time that I do it, I'm going to loop over each number. So I'm going to make my new signal as a new list, right? And then every time I loop through, I'm going to create a number and add it to that list. So for digit 1, that's going to make a 4. That's going to go there for the first phase, and then append to that, and then start over again. So first I'm going to do loop over the signal length again, or I'm sorry, the first time. And then remember, we're doing like a nested for loop. So for each number, we want to loop over the entire signal. So for like the 0, you're going to loop over the entire signal. So that's what we're doing here. For each number, again, loop over the entire signal. So my new value is going to be 0 to start out, and I'm just going to add to that. So if it's positive, add it. If it's 0, add it. If it's negative, add it. And at the end, it should all work out. And then I'm going to, actually, I missed this last part, sorry. So basically, if you do the math on these, another thing that they throw at you is that, so when you do this math, it could be like let's say this was like 34. They only want the number in the ones column. So they don't care about the 34. They don't care about the negative number. If it's -4, it should just be 4. If it's 34, it should be 4. If it's 3004, it should be 4. So to get that, at the very end, I take the absolute value, and then take the modulo 10 of that, which is just going to knock off everything except for the ones column, which is a nice little trick that you can do instead of doing like a convert to string and slice or some kind of craziness. So we get the phase pattern digit for that loop, and so that is this crazy formula. The inner loop number plus 1 divided by the outer loop number plus 1 mod the length of the base pattern, which is always 4. That is going to give you that base pattern index. So that's going to give me the 0, 1, 2, or 3 for that. Basically, which one of these numbers I want. And then I get that value doing a lookup in that base pattern. And then I just do that multiplication that we talked about, add it to the new value, and then do the absolute value. So we'll go ahead and run this for part 1, and we'll do it with our input, and we're going to do 1 phase instead of 100. And what I want to do is I want to show you this base pattern real quick. So if you look at this, you can see it starts out, this is also going to account for the shift left of the pattern. So remember, for the first one, we don't want to start at 0, we want to start at 1. So you can see it does, for the first digit, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1. So this should be 8 digits. So 1, 2, 3, 4, 5, 6, 7, 8. So 0 is going to be the last one. And then the next pattern, it's going to double each number. So then we're going to do 1, 0, 1, 1, 0, 0, negative 1, negative 1, 0, 1. And then it's going to do 0, 0, 0, 1, 1, 1, 1, 1 with a final 0 at the end. And then the rest is just going to be all 1. So if we look at the pattern, you should see this. So there's that first one where it just alternates basically through the pattern. Then we start at 0, we get 1, 1, 0, 0, negative 1, negative 1, 0, 0, 0, 1, 1, 1, 0, 0, 0, and then a bunch of zeros, 4 ones and a 0, and then it's basically a bunch of zeros, a bunch of ones, all the way down. So this is for 1 phase. You can see after 1 phase we get 48226158, which is that number there. We can bump this up to 4. We'll comment this out. That gives us 01. Let's bump this up a little too. 010299498, which we can see down here. So all is looking good so far. Let's calculate some of these. So go up here and let's look at the last example that they give, and we'll do it over 100 phases. So you saw it took like a half second there. The first time that I did this, well, first let's see if that's right. 524322133. Yes. So the first time I did this, like I said, I had a bunch of nested for loops. I was like looping and looping and looping and looping, creating a new phase pattern list and all this madness, trying to get this answer. And for the actual input value, we'll go ahead and run that and see how fast that is. See, it takes a few seconds for it to actually crunch that 100 phases on that number. Remember how long that input value is. So there we go. It took about maybe, what was that, like 8 or 10 seconds? So 73127523. There we go. That's the answer. So that's great. It worked. My original solution with the loops everywhere and everything took even longer. It took maybe close to a minute or 45 seconds or something like that. So that was a little troubling right off the bat. But part 2 is where this all falls apart. So for part 2, they're going to say the real signal, okay, not that puzzle input, but the real one is going to be that puzzle input, which, if you remember, is this giant string repeated 10,000 times. So you're going to take this and make 10,000 copies of it and smash it together into one giant string. And that is going to be your input signal. And then they say you want to calculate this after 100 phases. Yep, after 100 phases. But there's a few things they're going to change on you here. So first, they're going to tell you that the first 7 digits of your initial input signal is going to be the offset. So what that means is you're going to take these 7 digits and you're going to skip, once you multiply this 10,000 times, you're going to skip 5,973,857 of them starting from position 0. So just like this is to position, I think 6, we would count to position almost 6 million and discard that. We don't even care about it. So that's kind of interesting right off the bat. The second thing is we only care about 8 digits. So skip that initial offset of like 6 million something digits, or just shy of that. And then you're going to get the new 8-digit message. So then take a slice from that in 8 digits and give us that slice. So they give you some new values here. This after 100 phases. So this is, again, going to be multiplied 10,000 times. That should become that. That should become that, so on and so forth. If you run this on part 2, so we'll check out just to make sure I'm not crazy and that this still works. This should be 53553731. Oh, I'm sorry, that's part 1. Let's do 2. Runs pretty quick. 53553731. If you try to do this with the solution from part 1, it will never finish. And there's a few reasons for that. First, if you notice, part 1 took like 8 to 10 seconds. Imagine if you multiplied the input by 10,000, right? So that's going to be crazy. That's going to be a massive amount of numbers. Something like 60-something million numbers, I believe. Just ballparking it. So this becomes like an algorithm problem and a problem of complexity and data structures and that sort of thing. So the original solution that I had that was like loops inside of loops inside of loops, that's just never going to happen. So if I'm creating a new phase pattern for each digit in here every time that I loop, you can imagine the orders of magnitude of time that it's going to increase for that solution. So basically, long story short, the big O of that is awful. It's like super bad. So what you have to do is figure out a way to calculate this very, very quickly. And it's completely obtuse. There's absolutely nothing that they give you in this input or instructions that tells you what you need to look at or try to do to figure this out. This almost is entirely something that you're going to figure out based on just staring at these numbers and trying to figure out some kind of pattern. So I think that's why 16.2 or part 2 is the most difficult thing I've seen so far. Not because the code is difficult. Like you can see, this code for part 2 is not long at all. It's 38 lines all told, including my examples. So maybe like 30, low 30s. If I smash this all together, including my print statements and stuff. But the problem is that you've got to figure out what the heck they're asking you and how to get that final result. So the code doesn't really matter for this one. However you do this in Python or JavaScript or whatever you're using, Scala, Excel, or whatever craziness you're doing, the real meat of this one is in these instructions. So looking at this pattern, basically, this is where I talked to the Coding Blocks folks and asked for help. I said, I don't even really care about trying to figure this one out on my own. This one isn't really fun to me. Just throw me some hints, throw me a bone so I can get this one done and move on with my life. So basically, this one, the first thing to note is that for the signal, for each time that you go through this, if you look at the first half of numbers, you can't really cheat it. You got to calculate based on the phase pattern because that's switching all the time. You can kind of notice that, like, here you've got 2 1s, and then 3 1s, and you've got 1 -1, and then 2, and then 4, and I'm sorry, yeah, 4 1s, 4 1s, 3 1s, 2 1s. So there's, if you're looking at the first half of the digits, so like the 1, 2, 3, 4, that's going to be slow to calculate because of the complexity of the pattern. If you look at the back half of the 5, 6, 7, 8, if you split this in half, which I would have never thought to do, but if you look at the back half of this, that's where things get interesting. So really this starts to come together if you look at the very last digit. So if you stare at this for a couple of seconds, you can see that we don't care about any of the numbers except the last digit. So 8 is pretty much always going to be 8 in this 8-digit sequence, which you can see in all of the phases, right? 8 is always 8. So that never changes. So basically what you're doing is you're going to calculate that last number. And then if you go backwards to 5, now you just need to look at, you don't even really care about 8 because that's still going to be 8 times 1. This is going to be 7 times 1. So it's going to be 8 plus 7 plus 6 plus 5. So 8 plus 7 is 15, so that gives you the 5. 15 plus 6 is 21, that gives you the 1. 21 plus 5 is 26, and that gives you the 6. So you can kind of see already, like, that's a heck of a lot faster than looping through the entire list of numbers for each iteration, right? But where that falls apart is the first half. So the key here is that when they tell you that you're going to do this offset, and that is going to skip, it doesn't tell you how many digits, but it's going to skip a certain amount of digits. Basically, if this is, I think this is like 32 digits long. We'll go ahead and bust out the calculator for this. So that's 32 digits long times 10,000. That's going to be 320,000. Now, if you skip the first, what is it? 1, 2, 3, 4, 5, 6, 7. If you skip the first 303,673 places for that, trim off the first amount of those. As far as how many numbers that is now going to give you, so you're going to go from a number that is 320,000 long to a number that is minus 303,673 long. So you're going to go from a number that's 320,000 digits to a number that's 16,000 digits. So what does that matter? That matters because what that means is that you're never, ever, ever going to have to worry about the first half of the digits. So the first half of the digits where you're having to do all this complicated math doesn't matter because you don't even care about it. You're getting rid of it. And because the digits are always going to be the same place values, you don't really have to worry about that messing up your algorithm. So that's the trick or the secret to day 16 part 2. Is to just basically ignore the first half of this problem and look at this pattern of counting backwards through the back half of it. So you don't even have to worry about splitting this into halves in your algorithm or whatever. You just need to know that by the time that you get to those last numbers that you actually care about, your pattern is going to be the same all the way down through all of those digits because you've trimmed like 90% of them right off the bat. So you can calculate the entire thing very quickly by doing that algorithm of like 8 plus 1 plus 5 plus 5. That's a heck of a lot faster than looping through phases and all this madness and doing nested for loops and stuff. So if you look at that code, I get my input string. I look at my amount to skip, which is going to be the first 7 digits of that. I create a new string. I just loop over range 10,000, and add to the new string the same input string, so just duplicate it 10,000 times. And then I do a slice to get the remaining digits that I need to calculate. Right there. Then I do a nice list comprehension in Python. So I would use like a map in JavaScript, but if I say like for each character, perform an int operation on it in the input string, that's going to give me a list of digits, of integers. And then I loop over my phases, and then I'm going to loop backwards through the digits. So we're looking at this example. I'm going to start at 8, and that's going to give me value 8 at the end. Then I'm going to look at 7. I'm going to add 7 to 8, and that's going to be 15. Mod 10 will give me 5. Plus 6, so on and so forth. So that's what I do. I do this backwards loop. With Python, it comes out pretty nice because range will let you step backwards. So I can start at the end of the signal. So that would be the length of the signal is 8. In the example, -1 is 7. So start at 7, move backwards to 0 because the end of the range isn't included, and then step by -1. So go backwards. So it's going to go 7, 6, 5, 4, 3, 2, 1, 0. Or however long the list number is. It ends up being like 16,000 something. So from there, I have my new value, which is just going to be a placeholder. I'm going to say if that's not there, go ahead and set it equal to whatever that signal is. So that would be 8 in the example we were looking at. If it doesn't, add that signal to it. So 8 becomes 15, becomes 21. Do the mod, and then append it to the second half signal. So that's just going to be an empty list. And then at the very end, I just reverse that, and that's my new signal, basically. And then after 100 phases, I just do that slice of the first 8 digits, and that's it. You're done. So if you run this, you can see it takes a few seconds, but imagine the input sequence of numbers is multiplied by 10,000. So it's a absolute massive amount of information. There's probably a faster way to do it than this example that I have, or my solution, but there we go. Mainly it doesn't, like the code isn't as important, it's the algorithm that you're doing. So if you're trying to loop over all those numbers, like the complexity of this and the time that it would take would increase exponentially. If you're looping over things and going through all these values and bothering to loop over these zeros and stuff like that, that's going to make this take longer and longer and longer to run. And if you use the part 1 algorithm, it'll never finish. So that's basically it for day 16, part 2. We can sanity check myself. 802-844-20. That is what we got at the end. Yeah, day 16, I'm not really satisfied with that one. I don't really care for the puzzles that are, I don't know, they're like, you wouldn't have got that one if you hadn't happened upon that pattern and just stared at those examples for God knows how long it took most people to get it. Even having somebody explain this to me, it still took me hours and hours to get this, just thinking about it and thinking about it and thinking about it, and not really understanding what the problem was asking and what was happening. So I've seen the next couple of days. 17 and 18 look pretty cool. There are some maze pathfinding stuff again, so I'll probably be able to do some cool visualizations for that kind of stuff. So that kind of thing is exciting and makes for great GIFs and great videos and stuff. This solution, not so much, but yeah, so hopefully I can get those solved. I'm going to work on them a little bit tonight, but yeah, that's all I've got for Advent of Code. Like, subscribe, follow, all that good stuff. Hit me up on Twitter. Let us know what you think of the videos, and I will see you in the next one. Bye.